the same test. Good news is the worst is behind you. After this, it's all downhill. Well, maybe not exactly, but questions, ones you'd like to see? Yes, Priya.
27.
27. Do you know what that is, or do I need to?
I can.
So we're headed towards a chapter test that is going to be a week from this Friday. And then, because we tilt our whole schedule backwards, because we have to finish everything in time to still do an intensive 3 to 4 week review for the AP exam, which is May 4th. So our whole calendar gets tilted kind of, because we aim to end on May 4th, although technically it'll end that following week when you take your year-end final. So that Tuesday, May 4th is going to be the AP exam, which means we will finish teaching all of the new material probably around the beginning of April. And so that puts kind of our semester halfway point, like in a couple of weeks here. So we're going to take a chapter, it's like death by testing here. So a week from Friday, you're going to take a chapter test, and then the following week, you'll take your semester final exam. So we'll do that still here in December, and then we'll start on what's kind of second semester material, although we'll keep the grades in here until we get closer to the actual end of the calendar semester. But it's kind of tilted a little bit, so most of it happens on the front end. Priya.
Okay, so water is being pumped into a vertical cylinder of radius 5 meters and height 20 meters at a rate of 3 meters cubed per minute. How fast is the water level rising when the cylinder is half full?
Okay, so let's draw our picture here. Here's our cylinder, and the radius of the tank or the cylinder here, these are all meters, I think you said. So the radius is going to be 5 meters, the height is going to be 20 meters. I can even have new water, this is so fun. So we can, inside here, we're pouring water, so water takes the shape of whatever container it's in. So we have a cylinder of water sitting inside the cylindrical container, okay? So we know that these are the rate and the height of the actual container. This is water that's going in at 3 cubic meters per minute, and this is a clue as to what this is. So in the language of calculus, what is this telling us? This is a rate of change, which we know to be the derivative of the volume, because it's a volume measurement. So we have the V dt, and this water is going into the tank, so it's going to be a positive 3. So that's what that's telling us. Now we want to know at what rate is the height increasing when it is half full. So what is it we are looking for here? dHdt. It's a rate of change of the height. So dHdt is what we're trying to find. And we want to know that when it is half full. Well, when it's half full, what is its height going to be? 10. So that's there. Okay? Now the volume of a cylinder, you don't have to memorize these. These will always be given to you. The volume of a cylinder is pi r squared h. Okay? Now, our radius, so we're talking about not the radius and height of the container here, but we're talking about the radius and the height of the water that's being poured in there. Okay, that's what's changing here. Now, is the radius changing with time? No, it's fixed because it's stuck being that 5 because it's inside that container. So that is not a function of time. So we can plug in the 5 for the radius before we differentiate, which is good news, because then otherwise we'd have to do a product rule derivative. And we'd like to avoid that if we can. Now, the height is changing with time. The volume is changing with time. We can differentiate this, but can we plug in the 10 first and then differentiate? No, because then we lose the fact that h is in fact changing with time. So we're going to differentiate first, then if we need to plug in the h. So we're going to take the derivative with respect to t. So this becomes dv dt, the derivative of volume with respect to time. This is going to, I left out pi, I'm going to sneak it back in there. So that's going to be 25 pi times dh dt. So this is what we're trying to find. We know the dv dt is 3, so we can plug that in, and we can solve that for dh dt. So it's weird, but we're going to divide by 25 pi. So that pi is in the denominator. And that, we didn't now would ask for it, but the units would be, since it's h over t, that would be in meters per minute. Okay? Anything else?
Can we do 35?
Yeah, do you know what that is, or
No, I don't have none of those.
Priya, do you still have it?
A cone-shaped coffee filter of radius 6 centimeters and depth 10 centimeters contains water, which drips out through a hole at the bottom at a constant rate of 1.5 centimeters cubed. A.
Cube per second, is that right? Did I get the time right?
Correct.
Okay.
A. If the filter starts out full, how long does it take to empty? B. Find the volume of water in the filter when the depth of the water is 8 centimeters. And C. How fast is the water level falling when the depth is 8 centimeters?
Any in particular, or all of these?
All of them.
All of them, okay. So we have this cone-shaped filter, and so we're going to put water in there, and it's going to take the shape of a cone also inside there. And this water is leaking out. It's dripping through at 1.5 cubic centimeters per second. So again, what does this 1.5 represent? That's the dV dt. And because it's making that volume decrease, we're going to call that our negative 1.5. Is that okay? Let's see, we want, I'm trying to read my own abbreviation. Is that, how long does it take to actually empty? Is that right? So so to empty, it's emptying at 1.5 cubic centimeters per second. So when it is full, the volume of a cone is 1/3 pi r squared h. So when it is full, that volume is going to be 1/3 pi. The radius we said was 6 squared and the height was 10. So when it is completely full, we can say 36 divided by 3 is 12 times 10 is going to be 120 pi cubic centimeters. Is that okay? And we know that it's going to leak out or drip through at 1.5 per second. So we want to know how long will it take, what's the time for those two equal each other, for all of this to have leaked out. And so that is going to be there, which I think can go onto your calculator probably.
Would it be negative?
Well, it's a time value. So it's true that the volume is leaking out. So we're trying to say, you know, when does the amount that leaked out equal the amount that was in there to start with? So I don't think the negative really we need at that point in time. Or if you did, it would be, I guess you could do it this way. This might be maybe the more descriptive way of saying it is, you know, the volume minus what leaked out is equal to 0. When's the volume going to be 0? And then you're showing the negative part there. That okay? Okay. And I think if I'm reading this right, we want to know what is the volume when it's 8 centimeters, is that right? So then it's going to be, so what we want to do here is imagine now, so we know that the container, the container has a radius of 6 and a height of 10. Now, this makes a triangle. The container makes a triangle. Inside there, the water, which is going to be changing with time, has a radius and a height that are both changing with time. So as that water leaks out, that triangle of water is changing with time. But always, these triangles are going to be similar. So back to your geometry days, if you have two angles that are congruent, so they both have right angles, they share the angle here. So by angle-angle similarity, this big triangle is similar to the triangle of water. That means that their side lengths are proportional. And so however you want to write that, we can say that the R over the H in the blue triangle of water is equal to the radius and the height of the container. Are you with me there? So that means we can multiply the H to the other side and say that, and if we want to reduce that to make the numbers a little easier to work with, the radius is 3/5 of the height. And that's true no matter how much or how little water is in that conical filter. Is that okay? This is key that we can use the relationship here to make our formula here now have only one variable instead of two before we go to differentiating it. And so we can avoid using a product rule, which is going to make our life significantly easier. So then our volume, which was just 1/3 pi r squared h, can now become 1/3 pi. The radius we can replace with 3/5 h squared times h. Is that okay? So then we can say then that this is going to be, oh, let's see, we can cancel, all right, 1/3 pi, that's going to be 3 squared over 5 squared. H squared times h is going to be h cubed. We can cancel one of those h's, so I guess we'll get 3 pi over 25, h cubed is our v. See where all that came from? Okay. Now, this is what they're asking for in B, because they want us to simplify. We want to write this as only depending on h. So B is a function only of h now. And now we can say, how fast is that height decreasing? That is, we're looking for what is dh dt. At the moment when the h is equal to 8, when the height is 8 centimeters. So now, this is what we're going to differentiate with respect to t. So we'll get our dv dt, and the 3 pi over 25, well, that's just a constant. It's just hanging out. We're going to take the derivative of h to the third, which is going to be 3h to the second, and we know h is changing with time. It's a function of time, so times its derivative with respect to t. We can plug in the 8 for the h. So this is 3 pi, this is going to get ugly. We got 3, and we got 64 times dh dt. And the dv dt we said was negative 1.5. I'm hoping something is going to cancel here. So I'm going to call it a negative 3/2. Is that okay? Oh, like the looks of this. We multiply by the reciprocal. So I guess we'll get to cancel one of those 3's. I'll see. I don't think anything else is going to cancel, is it? So I think we're going to get 25. This is going to be up on top. All of this is going to join that in the denominator. Trying to think of the best way to do this. See, that's 180 and 12 is 192. If we double 192, that's 388. Is that right? Does anybody care? 388. And that's going to be our HDT, if I did that right. And that's going to be in, what is our units? Centimeters per second. Is that okay? Crazy. Anything else?
Maybe 37.
37? Okay, Priya, you're on again. A designated reader.
Grit, which is spread on roads in the winter, blah, blah, blah. They are in the shape of a cone. As grit is added to the top of the mound at 2 cubic meters per minute, the angle between the slant side of the cone and the vertical remains 45 degrees. How fast is the height of the mound increasing when it is half a meter high?
Okay. So we have, oh goodness gracious. So this is we're pouring grit or something onto this, is that right? So it is forming a conical pile. And so as we pour more and more on here, this is how much we're pouring on. The pile grows, but it maintains its conical shape all the time. Okay? So this 2 cubic meters per minute, what is that in the language of calculus? Yeah, that's our dV/dt. So we know that that's going to be a positive because we're adding grit to the pile. Now this whole theta equals 45. We'll come back to that in a minute. We want to know how fast is the pile growing. So what is the dH/dt when the h is a half or 0.5? Okay? Now, what we're going to say here, so this theta equals 45 degrees. Let me put that in a different color for a moment. So if we look at this right here, this is our angle theta, and that's always 45 degrees. So if that is always 45 degrees, what kind of a right triangle is that in spite of the way it looks in my picture? 45, 45, 90, which is also known as, what about the side lengths? They're equal, so it's isosceles. So a 45, 40, it must be a 45, 45, 90. That's what that's telling us. And if it's 45, 45, 90, then that means that these sides are the same. Does that make sense? Which means that this is the radius, and that's our height. So that means the radius is equal to the height, always. This is good. So our volume of a cone is 1/3 pi r squared h. But because we know the radius is equal to the height, we don't have to treat this as two different functions of t. We can replace the r by h, and our volume is going to become pi over 3 h to the third, which is going to make our derivative way, way simpler. Does that make sense? Okay. So, I think we're ready to actually differentiate this thing. So differentiating with respect to t is going to make that dv dt. We're going to get pi over 3. That 3 is going to cancel that. So we'll get pi h squared times the derivative of the inside function h, which we're going to call dh dt. Okay? And we know the h is going to be a half. So we're going to get, and the dv dt we said was 2. So we have 2 pi times a half squared times dh dt. So the half squared is a fourth. We'll take that pi over 4 and multiply by the reciprocal. So that's going to become 8 over pi is going to be our dh dt, and our units are going to be meters per minute. 8 over pi meters per minute is how fast that height of the pi was growing when it's half a meter tall. Am I crazy? What else?
Can we do 33?
We can. All right, Priya.
33. A ruptured oil tanker causes a circular oil slick on the surface of the ocean. When its radius is 150 meters, the radius of the slick is expanding by 0.1 meters per minute, and its thickness is 0.02 meters. At that moment,
Wait, hold on. Thickness, I'm sorry. Thickness was how much?
0.02
0.02? Okay,
meters.
gotcha.
A, how fast is the area of the slick expanding? And B, the circular slick has the same thickness everywhere, and the volume of the oil spill remains fixed. How fast is the thickness of the slick decreasing?
Okay. A lot to kind of unravel here. So we have a circular oil slick, but it's got a little thickness to it. So that means there's going to be a little volume to it as well. So the area of the top part, but with the thickness there, it becomes a volume also. So when we are looking for the radius is increasing at 0.1 meters per minute. So in the language of calculus, that's telling us what? That's the dr dt. And that's going to be a positive 0.1. The thickness is 0.02, that's constant. We want to know how fast is the area changing first. So first we want to know the dA dt. Then we're going to come back and we're going to talk about the volume, but that's a separate question. Okay, so the area of this circular spill is going to be the area of a circle, which is pi r squared. So we're going to differentiate this with respect to t. So we're going to get dA dt is going to be 2 pi r dr dt. Is that okay? And we are looking for the dA dt, and we know the dr dt is 0.1, and we know the radius is 150. So our dA dt is going to be 2 pi times 150 times 0.1. Is that correct? So 2 times 150 is 300, times 0.1 makes it 30. So that's going to be 30 pi is dA dt. What would the units be on a dA dt? You got meters and minutes. Meters squared per minute. Good. Okay. Now we've got, now we're going to look at the volume aspect of this. So the volume, this is like a real thin cylinder. So our volume is going to be pi r squared h. Now, the volume is going to be a constant. So our, what does that tell us? Well, let me leave it as, I'm going to say volume is just a constant. And I'm going to call it maybe V sub 0. It's going to stay the same. Okay, and so we have this now is not changing with time, is going to be pi r squared, which is changing with time, and the thickness, I'm going to call that h, is also changing with time. You all right to that? So we're going to differentiate this with respect to time. So if the volume is constant, what is its derivative? 0. Now we've got pi times r squared times the first, we're using our product rule. The first times the derivative of the second, plus pi times the second, and the derivative of r squared is 2r dr dt. You with me there? Now we're going to use the information we've gotten before. So the radius is still at 150. We're looking for the dh dt, that's what we want to find. Is that okay? We've got a 2 pi, the h was, do you know that? I think that's still the, do you know? Oh, the thickness is 0.02, I think. So I think we're still at that right now. And the radius is still 150. And the dr dt, I think we can steal from what we were given, that was 0.1. Okay, and we're going to solve. So I'm going to stop here. You can solve for that. I have, this is fine that we took up the whole class doing this, because I wanted to stay on related rates. I have, we're going to spend the next 2 days still on related rates. And if we if we have some time tomorrow, we'll also maybe revisit optimization. But I have a related rates worksheet for you here. It's got the answers in the back. These are tough, and there's no new assignment for tomorrow, so it's kind of like a 2-day assignment. But you might want to check, there's at least one kind of problem, like a shadow problem, that we haven't done an example of yet. It's going to involve similar triangles that you might want to watch or check out the support video on this to get an idea of what that looks like. All right.